Good. Okay. So we're talking about, I think, chapter 3. What, part 2? Okay, chapter 3, part 2. I think this one we talked about it last time. Yes. And we said, how can I get rid of this one here? I didn't need it here. Just put it somewhere here. Huh? There is hide? Yeah. Just I click hide? Yeah. Hide. Okay, hide, it works. Okay, good. So this is what? This is the stiffness metric for truss member in 2D, isn't it? So for each member you have to define E, A. We saw the table, and do you have a homework on truss? Not yet. Okay, don't worry, you'll see it tomorrow. Okay. We talk about this, right? Remember this? What is this? This is calculating C prime, and you multiply by the displacement to get the stress. Remember, C prime is a vector, a row, and what? And the displacement is a vector, right? Vector here. Oh, this is a vector, and you multiply a row by vector by column. You get scalar or what? Scalar. Yeah. Row by column, you get a scalar, and this is the stress. So always you need to define, and there is a formula for C prime. And you can do this for each member. We did this last time. We did this. Oh, this is the global, and we solve this, and we calculate the stresses. After you calculate the stresses, how do you check if your answer is correct or not? Because sometimes you calculate stresses and you are happy, you jump up and down, and maybe it's wrong. How do you check? You come to the joint here. Look at the joint. This is the joint. You come to this joint. You take the stress of member 3 and you multiply it by the area. You take the stress of member 2 and you multiply it by the area. And you take the stress of member 1 and you multiply it by the area. That will give you forces. And then you take a projection, summation of Fx and summation of y. Joint method, Truss, CE201, right? So it's easy. This is what he did here. And he found that after he calculated the stresses, you see, this is stress, look, stress, and this is area. Stress times the area is force. So he got everything in equilibrium. Okay, what about this problem? I have to speed up because now we understand the method, okay? Okay, let me put this like that, okay. Now, what is it? Determine. So truss 2 members. We talked about this last time, right? No? Just stop, but not, okay. Just stop, okay. This is 2 bars. Determine the displacement in the y direction. One of the common mistake, always you will think that x is horizontal, but here x is vertical. Y is, you see the direction? X is positive up, y is positive to the left. This is very important when you want to determine the displacement. Okay, the load is 1,000 kilonewton. Maybe you need to multiply times 10 to the power of 3. Settlement. This joint one, it goes down 50 mm in the negative x direction. E is given and A is given. And all the members, they have the same E and the same A. And the length, can you find the length for each member? 3, 4, 5. Right? So this is 4 and this is 5. Okay, anybody tell me what to do? We want to determine the forces in the member, but due to the load and due to the displacement. Tell me the procedure, because that's first you need to find what? In local or in global? Global. C square, CS, all of this. This is the elemental stiffness matrix in global. So you'll find K1, which is what? 4 by 4. You will find K2, which is what? 4 by 4. Okay, can you number this? How do you number? Element number 1. How do you? Element number 1.
Element number 1, 2. Or 2, 1, 2, 1, 2, 1.
So you'll put U1 U2, right?
Yeah.
U3, U4, right? X and Y. Okay, so it will be U1, U2, U3, U4. U1, U2, U3, U4. Okay, for the other one. Again?
Yeah.
So your local axis is going from 1 to 2 for member number 1. For member number 2, it's going from where?
1 to 3.
1 to 3.
Okay. But remember, the direction of the angle is very, very important. You see, this is now X, Y, global. This is X, global. Okay. Now, I can use another color for the local because you need to find what? You need to find theta, sine theta, and cosine theta. Okay. For element number 1, we said this is the local, right? So this one here, how we put X? Okay, anyway, you just put X along the member. Small x. Where is Y? Maybe Y here. Okay, what about member number 2? X along the member. This is X. And what about Y? Call this is X1, Y1. This is X2, Y2 for member 2. Because now you need to find theta. Okay? Can you tell me for member number 1, what is theta? And for member number 2, what is theta? Because this is going to give you the stiffness. What do you think the angle between? What do you think? Number 1. How much the angle? Did we give you the angle? The angle here, how much? Theta is how much?
No, they give us the length, we can find the theta.
We can find theta.
Yeah, we can find it.
From geometry, right?
Yeah.
Tan inverse of 3 over 5. Okay. So how much theta? How much here? How much this angle? Bring calculators always, okay? What is the angle here? According to this figure, theta will be equal
0.5.
how much?
0.54.
0.5. Are you sure? Degrees. Always theta in degrees, right? 0.10. 63.1. So do you think that theta 1 is this one? 63.1? If you think so, what is theta 2? Theta 2 how much? 90. Always like this, like this. Theta here is 90. Okay, then if you find this, you can find the stiffness. I think the remaining is just mechanical, right? Okay, let us see. Point 6. So you take cosine of that 3 over 5. Is this correct?
Yeah.
Sine is this. So you just put it, you multiply it by EI over L. So this is K1, U1, V1, U2, V2. Okay, what about, is it correct?
Yeah, correct.
Theta is 90, cosine 90, 0.
Yeah.
We got K2. Okay, what do we do next? We find K1 and K2. Assemble. You assemble the global stiffness, right?
Yeah.
This is the global stiffness. U1, V1, U2, V2, U3, V3. F1X, F1X, F1Y, F2X, F2Y, F3X, F3Y. You should know how many quantities you should know. 6 quantities you should know, right?
Yeah.
Because there are 12 unknown, assuming the displacement is unknown and the forces are unknown. So you have 6 and 6, 12. But there are 6 equations. You should know 6. What are the 6 that you know? Can you tell me?
Go back to the drawing, so you remember the number.
Okay. Tell me from here.
U2, V2.
I think U2, V2 is 0, right?
U3,
U3, V3 is 0, right? What about node number 1? Which one is 0? Is it U1 or V1?
We don't know it.
You don't know?
We don't know.
Which one you know? You know U1 or you know V1? You know U1. U1 is 0 because it's vertical. You don't know the V1. So it means everything you know except V1. Huh? So it means what? Only V1 you don't know? So U1 is not 0. This is the thing. U1 is not 0, but V1 is unknown. Okay. Remember this. Okay. So what do you want me to write here? So I will use the pen here. Okay, pen, or let's use laser. So U1 minus 50, right? Minus 50 mm. V1 unknown. 0, 0, 0, 0. Okay, can you get me one equation with one unknown from this equation? Okay, how do you extract? This is very, very important. I want one equation with one unknown.
F1y.
0.36.
F1y equals to 0.48 times of U1 plus 1.89 times of V1.
Okay. I think F2x,
F1y.
F2x is unknown, reaction.
Yeah.
F2y is unknown, reaction. F what? F3x is unknown and F3y is unknown. There is F1x and there is F2x. Which one you know?
F1y.
You know F1y?
Yeah,
F1y? F1y horizontal, how much? How much? No, there is applied force. Is it positive or negative?
Positive.
Is it to the left? If to the left, it's positive. So it's what? 1,000 times 10 to the power 3. Because it's kilonewton, right? Okay, this one here. Okay. What about
That
top?
is 0.
0? Unknown.
Okay.
Unknown,
Yes.
right? F1x is unknown. So this is F2y. Okay, this is equal F2y equals
F1y.
Yeah, it's F1y. Yes.
F1y.
No, that is F1x.
F1x. This is
And then there is F1y.
Unknown.
F1x.
Then there is
That's the
F1y.
second one. F2, 1,
F1y.
F1y equals
I will not put F1y, I'll put the value. 1,000 times 10 to the power 3. Is this good? It
Yeah.
makes sense, right?
Yes, sir.
Okay, now tell me the values here, the U's.
U1 is
Okay, U 0, 0, is it 0, 0? What? V?
V1 is unknown.
V1 is unknown. U, minus, down, minus
50.
minus 50. Okay, how do you find V1 equation, one equation with V1?
So the second.
So you have to go to the second equation. In the second equation, you write 1,000 times 10 to the power 3 equals,
0.48
now you have to
times
multiply
of
the second
minus 50.
row by this. So you take this
0.48
element and you
multiply
multiply it by minus 50. You see? Minus 50 times, how much is there?
0.48.
0.48.
Yeah.
Symmetric. Here, 0.48. And then
1.89 times of
plus,
V1.
is it plus?
Plus
1.89
89.
times.
V1.
Can you solve for V1?
Yeah.
And once you solve for V1, that's it. Huh?
Yeah, exactly.
Multiply by EI over L. EI over L. All this equals 0.
Only this side. Only this side.
Huh?
Only the right side.
Only this one here, right? Okay. Only this quantity, right?
That side.
Okay,
Over
this
here,
side.
yeah.
Okay,
You
good.
have L by-
Very good. Now we can solve for V1, right? Once you solve for V1, straightforward, right? Look at it. Is it what this is what we did? Is this what we did? P is equal to this. And then you solve for V1. How do you solve for V1? You move this to the other side. When you move this to the other side, you will get what? Negative, right?
Yep.
Is this okay?
Yes, it's okay.
No, it's not okay.
Why?
Because this is one quantity minus another quantity. V1 is equal to this.
Because he did not substitute.
Huh?
It will substitute the value of P.
No, I'm
right?
talking about
And
the
then-
values. The values, there's minus here.
Yeah. We substitute, we will get the values.
Substitute minus.
Substitute B.
From what this 25, because you multiply EA times L, right?
E over L.
Okay. Then you find V. Once you find V, you go and substitute in here, and then you can find the forces. Now this one here, F1x and F2x is what? The reaction, right? Of support 1. Then you can go to element 2. Wow, what about this one? If you have this one here, this is combination of a truss and spring. Is it hard? Combination of truss and spring.
We just have to form.
You need to find K for 1.
For
Okay, K for 1, how many K for 1? Tell me, what is the size? It will be 4 by 4, right?
4 by 4.
Very simple. For 2, 4 by 4. Okay, for K3,
2 by 2.
how come you add, you have to make it 4 by 4?
We'll add zeros.
You add zeros, 0 row, 0 column, 0 row, 0 column. Okay? Let's see that. This is K1. Once you define theta, that's it. You can find K1. You define theta, then you can find what? You can find K2. Let's see K3. Look, the first row is 0, and the first column is 0. The fourth column is 0. Similarly, the rows. Why? Why we put U1 for 0 and U4 0? Because spring can take either tension. There is no lateral displacement in the X direction, right?
Yeah.
Look. This is the spring. Look at the X. This is X horizontal. This is the spring. Spring is vertical. It can move in the Y direction. So you can say U1 for spring is 0 and U4 for spring is 0. And you have to know that it is not EA over L. It should be K minus K minus K. Yeah. Okay. Then what to do after that? You just have to assemble and you put boundary condition and find for the stresses. I think this is trivial and you are bored with this because this is way below your level. This is so CE201 and CE203 structure analysis. This is undergraduate, right? But it serves to go to 3D. So let's go to 3D now. Okay, 3D. How do you go to 3D? We have to go to the website and we have to download. Okay, let me see. Okay, where is it? I should roll this down. What do you think? Chapter 3, part 3. Okay. Is it shared already?
Yeah.
So once I open it, it's shared automatically. Okay. Okay. Continued, right? Very good. So, are you sure this is we have done that, right? This one is okay. Here we go. This is now 3D. In 3D, we are going to transform basically the local stiffness from local to global. This is local. In space, if you have a truss, so what is the local stiffness? It's the same thing. There is either tension or compression. It is 2 by 2. Whether it is in 2D or 3D, it's the same thing. So if I put a member here, it's 2 by 2. If I put the member like that, it's 2 by 2, local. If I put it from here to here, it's also 2, local. Now, how do you go from local to global? You remember, you need to multiply by transformation, transpose and transformation. T transpose and T. Anybody can give me an idea what do you think? CX, CY, CZ. Have you heard about direction cosine of a vector? Cosine alpha, cosine beta, cosine gamma. Alpha is the angle between the vector and the x-axis. Beta is the angle between the vector and the y-axis. I think I have to draw it. You know it. MashaAllah. If this is x, y, z, and if I give you this is a truss, and I give you this angle, and I give you this angle, and I give you this angle, or you can find it. This is called alpha, beta, gamma. This Cx is cosine alpha. Cy is cosine beta. Cz cosine gamma. That's it. So you need to determine the 3 angles. How do you determine the 3 angles in space? We'll see. But now you understand. But before you do that, you have to multiply these 3 together. I asked you to do this in MATLAB, right? Have you done it? Okay, this is your next assignment. Okay, can you multiply these 3 matrices together? What would be the size of the matrix? This is 6 by 2. This is 2 by 2, and this is 2 by 6. So you get what? 1 by 6? 3 quantities. 3 quantities. The first quantity is 6 by 2. 2 by 2. 2 by 6. Cancel, cancel, cancel. 6 by 6. Okay, so you'll get 6 by 6 for the 3 dimension. It's here for 1 element, for 1 member. Because this is called the global stiffness matrix for the member in 3D. So it's in terms of what? In terms of 3 quantities, Cx, Cy, Cz, that's it. And this determined by what? By alpha, beta, gamma. Easy. Now you find the stiffness, you know the rest. Assemble, put F, put use, put the boundary condition, see what are the unknown, extract the equation, substitute back, get the forces, get the reaction, and then what? Get the stresses. Okay, let's see. This is an example. Okay, this you are going to do it using the software. And you will do it manual, not this one, the one in the homework. Okay, so this one you will do it manually. Okay, how do you do it manually? Okay, this is member number 1, member number 2, member number 3, and this is node 1, node 2, node 3, and node 4. Okay, and you have the area for each member, A1, A2, A3. Okay, how do you determine? Let's see how we can define K, K1. What do you think, K1? Anybody can tell me what is alpha, beta, gamma for member number 1? Yes. You see, what you see, this is the global axis here.
Yeah, we have to
manipulate the coordinates.
This one here is the global axis, X, the global Y, and the global Z. Okay, so you need to know the local here. Maybe you will assume what? Maybe this is 1X, maybe Y. Where would be Y? Maybe up, Y? Maybe this is Z? How do you do it? Huh? How do you do it?
So you need to use the coordinates.
You need to use the coordinate. If you start to be smart to figure out alpha, beta, gamma, you will not. You have to use the coordinates. So this one you told me it is what? 6 by 6, right? And this 6 by 6 composed of 4 submatrices. What this is lambda. This is lambda 4 by 4. This is what? 3 by 3. Lambda 3 by 3. Lambda 3 by 3. Lambda 3 by 3. So the 6 by 6, you can find it once you determine lambda, right? So this is 3 by 3. You put 3 by 3 here. You put 3 by 3 here. You take this 3 by 3, you multiply it by minus sign. It means you multiply all the element by minus sign. You put it here, and you multiply all of this by minus sign, and you put it here. Okay, then, therefore, determining lambda will be sufficiently to describe what? K. Look at it. The direction cosine of element 3 are given in general by Cx, Cy, Cz. What would be Cx? X4 minus X1. So your axis is going from 1 to 4, first of all, right? So it's directed from 1 to 4. So you have to take the coordinate of the head, you subtract it from the tail. So it will be X4 minus X1 divided by the length. Okay, what about the other one? Y4 minus Y1 divided by L. That's easy, right? Okay, and Z4 minus Z1 divided. So he found this, and he found Cx, he found Cy, and how did he find the length? Do you know what for the length? This square plus this square plus this square. He found lambda. That's it, 3 by 3. Then what to do? Now you can construct K3. You just take this, put it here, take this one and put it here, multiply this by minus sign and put it here, and multiply this by minus sign. I know you start to lose focus. You multiply this by minus sign and you put it here. What is this one? Is it EA divided by L? EA divided by L. So what's your question? Huh? How did you get L? If you know the coordinate, you didn't know to find the distance between 2 points? That's what you did. If you know the coordinate, you know the difference in the x square plus the difference in the y square plus the difference in the y under the root. Okay? Very good. Now, what do you think in the next slide? In the next slide, it is the same thing, but element number 1. What happened? How he found Cx minus 0.89?
Same formula, the last one.
It's the same thing. So it's going, what do you think for element number 1? It's going from where to where? You have to determine at each member which one is the I node and which one is the J node. For member 3, we said 1 and 4. For member number 1, it is what?
1 and 2.
Yeah, 1 and 2. So it will be x2 minus x1 divided by L, right? And y2 minus y1 divided by L. Okay, we found K for element number 2 and element number 1 and element number 2. Assemble. What is the size of the global stiffness? Can you tell me? What's the size of the global stiffness? Yalla. Yalla, what would be the global stiffness? This is what you have.
For one element, it is 6 cross.
I said global stiffness for the structure. For the element, it is 6 by 6. But now you will assemble it.
12 cross 12.
It will be what? Is it 8 by 8, 12 by 12?
12 by 12.
12 by 12. Okay, 12 by 12. But still, we didn't know how much we need to what? To extract from this 12 by 12. Maybe we need to extract only 2 equations, 1 equation, or 3 equations. Okay? So this is now 12 by 12. This is 12 by 1, and this is 12 by 1. Okay. So it would be what? F1x, F1y, F1z, F2x, F2y, F2z. And then F3x, F3y, F3z. And then F4x, F4y, and F4z. Okay, which one you know? Which one you know from the F's? Yeah, from the X. Okay, we'll come back to it. Let's go to the U's. Okay, maybe that's easier. U's. You come to number 1. which displacement you know and which one you don't know. It says here, roller preventing Y displacement.
So we know why.
So it's
We don't
preventing
know
the Y
X and Z.
displacement, means
We
it
don't know X and Z.
cannot go here like this.
We don't know X and Z.
So
So we know
U1,
F1.
U1 is unknown.
Yeah. U1 is
V1,
Zero.
0. What about W1?
unknown.
Okay, finish. Okay, go to the node 2.
Remaining we know all of them.
All of them unknown?
Zero.
Zero.
Yeah,
Zero. Zeros.
All of these zeros?
Yeah.
Okay, 0. It means we need to extract only 2 equations to solve for U1 and W1.
Yeah.
Only 2 equations. Okay? You have to make sure, since the unknown is U1, you should know F1X.
Yeah.
And since you want to solve for W1, what? You need to know F1Z. Okay. How much F1X?
F1X equals 0.
F1X.
Zero.
F1X is 0,
Zero.
0. Yeah, there is no force at the moment. It's 0. And then F2X, F2 what? F2, F1Z
minus 1,000.
Minus 1,000.
minus?
Yeah.
Okay, minus 1,000. Okay, so what to do?
1,000.
Now we have 2 equations.
Very simple, very simple. The first equation you will generate 0 equal, you take the first row and you multiply it by this column. You get one equation with U1 and W1.
Yeah.
And then you go to the what? The third equation, minus 1,000 equal, the third row, you multiply it by this, you get another equation. And then you solve for U1 and W1. Let's see if this is what happened here. Just mechanical, right? You see 1, and this is W1. This is U1, and this is W1. And then you solve for that. Once you solve for those displacement, then you can calculate the stresses, okay, for each member. And once you calculate this, you can check the equilibrium, okay? So keep going, okay? Use the symmetry of structure. If somebody give you this problem, how you will solve this problem? I give this at one of the major. I give this problem. Huh?
Symmetric.
Symmetric. Don't solve the whole problem. You have to use half of it. Symmetric. So if it is symmetric, how you will solve this problem? 1 is the same as 5. 3 is the same as 2. So how do you do it?
You just solve the upper half.
You just slice it. And instead of having this, you'll have only 2 triangle, 4 triangle, 1, 2, 3, 4, right? So when you slice it,
You just solve one triangle and it solves the entire thing.
no, you'll solve this triangle. You'll solve this 2 triangle. You'll slice it because there is no symmetry here like this, right? So it's like this. Okay, but now when you slice it, you don't only slice the load, but you slice the stiffness of the member. So if you are member number 4, or if you are number 5, they will cut you to half.
So even the area will be half.
One eye will be here and the other will be here. One leg will be here and the other leg. So your stiffness should be half. Your area is half, okay? And the load that is carry this will be half of the load. These 2 things, half of the load and half of the stiffness. This is very, very important.
What about the modulus B?
It's the same material, right? It's the same material. So, look at it. Is it 2P? Yeah, 2P. 2P. He put only P. Okay, good. What did he do here? He put roller here. Because if you slice it and leave it, it would fall down. Right? So you need to put support. What is the symmetry? When you say there is a symmetry here, symmetry, it means that node 2, it cannot go to the right and it cannot go to the left. Node 4, it cannot go to the right and it cannot go to the left. It can only move vertical. Node 3, it cannot go to the right and it cannot go to the left. So how do you model this in structure? By putting roller. Look, roller at 2, roller at 4, and roller at 3. Now I can give you this problem like this. Then you will feel good. But if I give you this problem like this, it's horrible, right? I can start with this, but I will not give you this. I'll give you this. So you know how to get this, right? Okay. How do you solve? No, this is 2D problem, right? Easy, right? 2D problem. So it will be what? Theta, C, and S. There is no CX, CY, CZ. Okay? So the size of each member is what? 4 by 4?
Yeah.
Yes, 4 by 4. K1, K2. We have to watch here, okay? Let's see. Which one is member number 1? Okay, this is member 2. Let's watch for member number 4 and member number 5. What happened? Watch this. 1 is okay. 2 is okay. 3 is okay because you didn't cut it. But you cut 4 and you cut 5 to halves. Let's see what happened. Okay. Stiffness for K1, it's okay. What are the 2 member?
4 and 5.
4 and 5?
Yeah.
Okay. What is this? There is half here. Did you see the half?
Yeah.
If you don't cut it, so it just looks like you just divide by 2. You take what? AE or EA divided by L. You just divide it by 2 or multiply it by 0.5
Yeah.
because you cut it. Because EA divided by L, it's K. So it's K over 2. And similarly for 5, you see, it's half, half, half. That's it. You can solve now the problem. And do you agree that the unknown will be 3 unknowns here? Do you think 3 unknowns here if you solve this problem? Do you think 3 unknown? Do you think 3 unknown here?
Yeah.
What are the 3 unknown?
Reactions at 1.
V2, V4, and V3. Because U2 is 0. Reaction. U4 is 0. U3, 0. Okay, you solve for the 3. All of them in the y direction.
So if there was a horizontal load, then there would have been the horizontal displacements also would have been unknown.
Where? In
The
which?
question if we had a horizontal load applied.
If you have a horizontal load, where? For example, where?
No, on the previous slide.
Where you have the horizontal load? On the top?
Anyway,
Like the top. You put load here.
On node 4, if we have a
On
horizontal load
what?
applied. On node 4.
On node 4.
Along with the vertical one, you also have a horizontal load applied.
Then this is not symmetric, right?
Yeah.
You cannot. You have to solve the whole problem. You see? So you could disturb the symmetry by just making 2p in this direction.
So
Okay.
then it is symmetric, like if we remove the vertical load, now it is symmetric like this thing, this thing.
Okay, but you told me both of them.
Yeah, okay, both of them are there, then it's not.
What you do, you just change it. Instead of this one, you just put it here, okay? Yeah. Okay. Always you think about the worst conditions. Okay, now أشوفكم كنتوا تطلعون الساعة.
Let's go to the worst definition.
Okay, you find the displacement. After you find the displacement, what do you do?
Forces of the
You just multiply. Okay. This is your task for next Sunday. What happened if you have, tell me now, what would be the boundary condition here? There is hinge here. You will tell me U1 0, U2 0. Here, always you have to define your displacement with respect to the global. Here, in the 3. This 3, if this is moving this way, it means it has displacement in X and it has displacement in Y.
Yeah.
So how to solve this?
We can take components of this displacement, solve for the components.
This is called incline or skew support, okay? You have to make transformation from, because you already know the support condition in global, in local, you have to do it in global. Already you know what are the displacement. Already U3 prime is what? Is unknown, but V3 prime is 0. Do you agree?
Yeah. Yeah.
Now you can transform this into, already you know this. How much U3 prime? How much? Unknown. How much this one? 0. And you put here U3. You see? You transform the displacement from local, which you know, to global. Okay? This will cover next class. Okay? But try to see how you look at this. Just try to see what you can do in this, and then there is examples. Okay, you just during the weekend try to enjoy it, and that's it. This is when you have what? Secure support, and that's it. This we're supposed to finish what time? 10:45. Okay, so let us discuss now about the homework and your experience. And I told you everybody should find a group. Who found a group now? Okay, who's going to work with you? You'll work together?
Yeah.
And I said the maximum will be 2 or 3. 2, right? 2. Okay, send me an email.
Sure.
That you and that you will be working. Okay. Okay, so we finished from 2. We have 22 students here. Okay. You work together? You work together? Are you happy with them? Okay, good. You work together? Fahd is not here. He didn't come today. Okay. Okay, you work together? Okay, good. هذا الابكس خلاص هذا الركن بالراحه if you teach it you will get promotion because he needs it. You are talking about the airspace ولا واحد ثاني غيره مش الملكي خلاص ولا الفرق زين work with them زين يعني انتهينا all of this done with whom you will work. Okay, we'll find something for you, don't worry. Okay. So finish. You finish, right? With whom you said? You decide. With whom you will work? You finish. With whom? Huh? You will work together? Okay, send me an email. How do you know him? Huh? From the same place? The same state? Really? Okay, so you work together. Great. So you did. Okay, anybody who did find a person here, raise his hand. Raise your hand. Raise your hand. Raise your hand. Okay. So 2, 4, 5. مين بعد غايب? Anybody is not here?
Yes, there is one person.
Yeah, Amin is not here.
Who?
Amin.
Amin? Who is Amin?
He was from.
The guy who's stuck.
Yeah, he's stuck in
Saudi.
Turkey.
He's Saudi.
He's Syrian.
There is another Saudi here. Fahd, right? So there are 2 missing.
No, one guy is already
Huh?
moved, right?
You're with him? Okay, so we finish with Amin. Okay, can you raise your hand? Those who didn't. 1, 2, 3, 4. Okay, what is your experience? What's your experience? Which software? Console. Right. Huh? Answers. so? So impossible to put you together, right? You are using you. You have to have somebody who can take by your hand, right? Okay. Do you know consult? You do know consult? Okay. Can you work with him and consult?
Me?
Yes.
No problem. Sorry.
He is hard work student. Okay, you're willing to cooperate. Okay. So what did you do in what? MATLAB. Do you know MATLAB now?
Yes. Next section, we have four arrows.
And you studied it yourself. It's good. He studied by himself and now he knows MATLAB. I think he will not fail you. Okay?
No problem. We will discuss after that.
It's okay. What about you? Can you work together? Are you mechanical? Seven. Mechanical? Oh, seven. Okay, answers. Why you choose answers? Okay, maths. Aerospace كانت نازلة. مين اللي درستها في زي اسمه درس؟ ليش اسمه يعني؟ إنسان بقى. ها. Okay, the battery is running.
Yeah, if it goes down, the recording will go away.
Even my battery also running. I'm running out of battery, just like the computer. Okay, so that's it. So you'll work together in ANSYS, okay? ANSYS, right? Okay. Who else? Okay. Are you coming with them in the same plane? If you come with them in the same plane, I will tell them to
So
join.
it will not oppose anymore.
So are you new here?
Yeah. Service stop.
Can you work with them? Exceptional, okay? But that's a big good project. Very good project with your three. Huh? What? You are all new? This is your first semester or? What did you choose now? First semester. And your first semester. You didn't know too soon and you are using somebody to save you. You cannot, right? That's it. He's confident that you have a lot of time and you have to divide the work among you, okay? What did he say? I didn't hear your word.
Maybe it should be better if we get someone who is familiar with such software.
One of the things that you have to learn is how to make public relation. You really need to know somebody else to teach you, right? Yeah, in the department, right? Okay, we have a party, I think it's civil engineering, that it's familiarizing people with themselves, things like that. Okay, so don't worry, okay? I'm here. If you have stuff, we can ask somebody to help you. If you have master and PhD student, they can help. So the three will work together, okay? Now what about you? We finish, right? Anybody? We sorted out.
Who's in the man? Who is in the middle? Be one or together.
Huh? Now you write your name, each group. Okay. Anybody has paper?
Yes.
Okay. You just write. Okay. We need this. Okay. How many groups now? How many groups? Now we need to have. Okay. I'll start with this row. أوقف التسجيل. Okay. Otherwise, we will lose everything. Okay, so shall I stop share?
Yeah.
Stop share and then close. Where the box? The box here, right? I click on this one.